All right, let's talk a bit about how we evaluate our multiple regression model once it's been fit and that we've confirmed that it looks like a pretty good reflection of how y and each predictor are related to each other. All right, so the first way that we can tell whether or not our model seems to be fitting the data pretty well is by looking at R squared. Now, we've talked about R squared in terms of a simple linear regression, and things really haven't changed much in the multiple regression context. R squared still gives the percentage reduction in the sum of squared errors when using the regression model to predict y rather than the naive model. So we know we have two competing ways of predicting y, basically ignoring anything about the x variables at all, and just predicting y from the overall average value of y in the data, y bar. So if we do that, that'll make errors. If we sum up the squared errors of that, here's the sum of squared errors when using the naive model to predict y. And the regression model is always going to do better. Whenever we have a regression model, you have a bit more flexibility to fit the data, and so the sum of the squared errors when using the regression model to predict y is always going to be a bit smaller. So if we look at the reduction in the sum of squared errors when going from the naive model to the regression model, and divide that by the sum of squared errors using the naive model, that is by definition R squared. So it's giving you the percentage reduction in the sum of squared errors when using the regression instead of the naive model. So R squared goes from 0 to 100%. The larger R squared is, the better your model fits the data. Now, important note, the model still has to be appropriate. A high R squared doesn't mean that the model fits the data well. There might be very subtle nonlinearities, but assuming that the model does accurately reflect how y and x is related and regression is an appropriate model, R squared tells you how well the model fits the data here. And so this is a rather clunky definition of what R squared is. Another way of thinking of R squared is it's basically the percentage of the variability in y that can be attributed to or explained by the model. So in other words, using your model to predict y gets you about 100 R squared percent of the way there to knowing the y value. Okay, just as an illustration, remember the naive model, we predict y from the overall average value of y in the data. So the naive model in a simple linear regression is just represented by a flat horizontal line. Here are the errors that the model is making. We square them, sum them up to get an SSE of 957. When we use the regression, well, the regression has more flexibility. It's going to get closer to the data points. The sum of the squared errors is going to be smaller. And if we look at that percentage reduction, in this case, 957 to 323, we get an R squared of 66%. So 66% of the variation in y that we see about from 10 to 50 can be explained by our model. All right, using the salary data set, we're predicting salary based on education, experience, and months. We see that the R squared, which R calls by multiple R squared, is 30%. So essentially using our model, taking into account education, experience, and months, we get about 30% of the way there to knowing what the salary of an individual is going to be. So just remember that R refers to R squared as multiple R squared. There's an adjusted R squared that we are just about to talk to. But R squared by itself is always going to be multiple R squared here. Okay, so R squared actually has a problem associated with it. It may not necessarily give a good measure of how well the model fits the data because it turns out that R squared gets larger whenever you put more variables into the model, even if those variables are completely unrelated to y. The reason why is that whenever we add a new variable into a model, well, we give the model a little bit more wiggle room to kind of get closer to those data points. So with a little more wiggle room, we fit the data better, so the sum of the squared errors that the model is making is actually getting smaller. Now, to demo this, let's imagine that we're trying to predict y from just a set of completely random, unrelated predictor variables. So in this simulation, I set up the random number generator, and I generate my y values. These are just random normal numbers with a mean of 5 and standard deviation of 1. And so they have nothing to do with anything. They're just generated all by itself. Now let's generate 10 random predictor variables. x1 is going to be 10 uniformly distributed numbers between 0 and 1. And same thing with x2, x3, x4, etc. So we see that by design, none of the predictor variables, none of the x's, have any sort of connection with y. But let's look what happens when we try to predict y using these predictor variables. So using just x1, understandably, we get a very small value of r squared, 0.5%. Not very impressive. If we predict y from x1, x2, and x3, well, r squared is about 24%. Adding in x4 and x5, r squared jumps to 43%. And if we add in x1 through x7, it looks like we have a really good fitting model with an r squared of 96.6%. And in fact, if we try to predict y from x1 through x9, we get a perfect fit. There's no error, and r squared is 100%. So r squared has this drawback that when we add in new predictors into the model, even when they're not related to y whatsoever, it makes the value of r squared get bigger. So what do we do about this? Well, instead of using r squared, a fairer number that gives a better idea of how well the model fits the data is r squared adjusted. And what r squared adjusted is going to do is it's going to take r squared and then penalize it based on the number of predictors in the model, basically penalizing it by how complex that model is. So there's a formula for it. We don't really care too much about it, but basically r squared adjusted is just the original value of r squared minus a penalty term based on how many variables are in that model. And so as the number of predictors increases, well, the value of r squared will increase only if the increase in r squared is large enough to offset the added complexity of the model. In other words, the penalty term. So for r squared adjusted to increase, that new predictor really does have to help out the model in a substantial way. And so rerunning this simulation but looking at the r squared adjusted when we predict y from just x1, x1 through x3, etc., we see that there's no associated increase, and in fact, the r squared adjusted values are negative. R squared is always between 0 and 1. R squared adjusted can be negative. A negative r squared adjusted means your model is just awful. And in fact, predicting y from x1 to x9, you can't even calculate what r squared adjusted is in that case. So when we're dealing with a multiple regression context, to really gauge how well the model is fitting the data, we use r squared adjusted because that adequately penalizes r squared based on the complexity of the model. Just throwing in random predictors always makes r squareds get bigger. So r refers to r squared adjusted as the adjusted r squared, and it's a much fairer measure of how well the model fits the data. Now, unfortunately, there's no nice interpretation of r squared. It's just a useful number. I can't interpret what it actually means in words. And like I said, r squared adjusted can be negative, indicating a really bad model. Now, when r squared and r squared adjusted are about the same value, that's actually a really good sign. That means typically that most of the predictors in your model are worthwhile. They're really adding to the ability to help predict y. Okay, a complementary measure to the r squared adjusted is the root mean squared error of the regression, the RMSE. Now, back in the simple linear regression context, the RMSE was the typical error made by the regression equation, and it's the same thing in the multiple regression context. It tells us how far off individual values typically are from the predicted values in the regression. So it's just the typical error that the regression makes. So R refers to the root mean squared error as the residual standard error, and you always want to look at it to see, okay, well, how well is my model fitting the data? What's the typical error that it's making? Once again, the root mean squared error is only going to be a useful number if that regression model is appropriate. All the assumptions seem to be met. So one thing to note about the root mean squared error is that whenever we add an additional predictor, we know that that's always going to make the sum of squared errors of the regression get smaller. More predictors, more wiggle room, the model's going to fit the data. However, the root mean squared error can get bigger if that additional predictor is bad, if it's not really helping to predict y all that well. So like r squared adjusted, root mean squared error really has a built-in penalty for the model's complexity. And so when you add in more predictors and you see the root mean squared error getting smaller, in some sense, those added predictors are really helping out the model. Okay, here's an example of our output. Where do we look? Well, we look down at the few last lines. The RMSE is that residual standard error. So in the salary example, we typically make an error of about $340 when predicting salaries. The R squared is 51%, so using this model, notice I've actually added gender into the model, I get about half of the way there to knowing what the salary is. Fair value for what the model fit is R squared adjusted, coming in just a little bit below 50%, so pretty good model there. So I'd say this is a pretty nice model. Not too large of an error, getting within a few $100s, and a pretty good value of R squared adjusted. Okay, so after we've determined whether or not our model is useful to us, if it has any practical significance, in other words, a low enough root mean squared error or a high enough R squared adjusted, we'd like to see, okay, well, is there any statistical significance of the model? Obviously, we can't have practical significance without statistical significance, so what does statistical significance mean in the context of a multiple regression model? And just like interpreting the coefficients, statistical significance means something very specific in the multiple regression context. So in a simple linear regression, the significance of a model and the predictor itself were tied together. If the model was significant, then X was a statistically significant predictor of Y. What does it mean to be a statistically significant predictor of Y? Well, it means that the model predicts Y significantly better than some random unrelated predictor. You're better off predicting Y from X than just from the overall average value of Y itself. All right, so in the multiple regression context, there's more aspects to statistical significance, and there's three possibilities. It might be the case that the model nor any predictors in it are significant. It might be the case that while the model is significant, we only have a sum of those variables being significant, one or more, potentially all, of those predictors being significant. Or it might be the case, and this will sound weird, that the model is significant, but none of the predictors are statistically significant in it. So let's actually walk through what it means to be significant and how we see these scenarios. All right, so what does it mean for the regression model itself to be significant? Well, in order to be significant, the model has to do better at predicting Y than a model full of completely random, unrelated predictors here. So, in other words, we have to be predicting Y better than just using the overall average value of Y, the naive model, to make our predictions. So the way that we'll do this is we'll gauge significance by looking at the reduction in the sum of squared errors when going from the naive model, predicting Y from the overall average, regardless of what the X variables are, to using the model to predict Y. So in this case, we see a reduction from 957 with the naive model to 323 with the regression model, and we need to make sure that this reduction can't just happen by chance from a model filled with completely random, unrelated predictors. So what we'll do is something similar to simple linear regression is we'll calculate a statistic called F. Now, I'm not going to go into too much detail about what the actual value of what F means. You basically look at the reduction in the sum of squared errors from the naive to the regression model, divide that by the number of predictors in the model, and then divide it by something else. But basically, we can think of the F statistic as some measure for how much the sum of squared errors has decreased, or alternatively, a measure of how big R squared is. So a value of F that's much larger than 1 is evidence that the model is significant. In other words, it does better at predicting Y than the naive model, or a model full of random, unrelated predictors. So the question is, okay, well, what values of F can occur just by chance? So if it's unlikely that the reduction in the sum of squared errors could occur just by chance, we're going to say the model is statistically significant. Specifically, we're going to say that a regression model is statistically significant if it's unlikely that a model using an equal number of predictors unrelated, independent from Y, would produce a value of F, or R squared, at least as large as the value observed in your data. So the bigger the value of F, the bigger the value of R squared, the more evidence that your model is doing a better job at predicting Y than just random predictors. And so the model is statistically significant if it's unlikely to get a value of F or R squared at least as big as what you've observed just by chance. Okay, now once again, before talking about how we determine this, remember that if we do find that a regression model is statistically significant, this does not prove a causal link between y and any of the predictors in it. There could be lurking variables, we could have made an error, etc. Okay, so how do we gauge significance? Well, we look at the p-value of the regression model. This is an important thing to remember. The p-value of the regression model is the probability that a regression containing an equal number of predictors that are completely unrelated to y, so basically a completely nonsense model, would actually give you a reduction in the sum of squared errors, a value of r squared, or an f value at least as large as the one that you measured from your data. So the sad fact is, even if we try to predict y from a collection of random unrelated variables, we get a value of r squared out that's bigger than 0. We get a value of f out that's bigger than 1. We get a sum of squared error reduction because any model gives flexibility and ability to fit data points. The p-value is the probability that we would get any of these quantities just by chance. So if that p-value is less than 5%, we say the regression model is statistically significant. It's unlikely, though not impossible, that a model full of random unrelated predictors would do as well as predicting our y values as our model. So we can say that our model is predicting y better than that model full of predictors unrelated to y. If that p-value is 5% or greater, the regression is not statistically significant. Essentially, there's nothing in your model that's helping you predict y any better than just a random set of unrelated predictors. All right, so how can we find this p-value? Well, once again, we can find this by simulation using the same method as we discussed with simple linear regression, randomly assigning y values to each individual and seeing what the values of f or r squared that result just by random chance. And we can actually get a value from theory as long as the regression model is appropriate. Those disturbances have a normal distribution. Okay, where do we look for the significance of a model in output? Well, once we run summary, we're going to look at the f-statistic line. So this is that f-statistic bigger than 1 is evidence that the regression model is significant. Here we see a value of 12. What's the p-value? Well, about 2 times 10 to the minus 5. So less than 5%, so we say the regression model is statistically significant. There's something in the model that is helping to predict salary better than just what random predictors might be able to get. Okay, so if the regression model is significant, that means something in the model provides some information about predicting y. So what we do then is we look at the p-values of the individual predictors. Now, these p-values of the individual predictors add a very slight amount of additional insight about the problem. Before talking about what that insight is, I'm just going to say what is significant, what's not. Well, we look at the p-value of those individual predictors. If the p-values are less than 5%, we say that the predictor is statistically significant. Okay, so what does it mean for an individual predictor to be significant in a multiple regression model? Well, it means something very specific. All right, we say that an individual predictor is statistically significant if the reduction in the sum of squared errors when it is added to a model with all the other predictors already in it is large. In other words, unlikely to have been produced by a predictor unrelated to y just by chance. So this is what we do. Basically, we imagine a model with all the other predictors already in it, and then we add the predictor of interest to that model. The sum of squared errors is going to get reduced because whenever we add in a new predictor, we give the model a little bit more flexibility. It's going to fit the data better. So when we add in a predictor, we're going to get a sum of squared error reduction. The p-value of that individual predictor is the probability that we would have gotten a reduction in the sum of squared errors at least as big just by random chance from a random predictor, essentially. And here's the rub. Unfortunately, the statistical significance of an individual predictor, I think, is probably the concept that's the least understood by the majority of the practitioners out there. There's a very specific interpretation to the significance of an individual predictor, and unfortunately, the significance is much less informative. It doesn't tell you as much as what you'd really like to know. All right, let me illustrate this by going through a few examples. So let's use the NFL dataset predicting the number of wins based on the number of offensive total plays throughout the season. So what we see that in a simple linear regression predicting wins from this one variable, this regression is statistically significant. P-value is less than 5%, implying that using the number of offensive total plays to predict wins does you much better than predicting wins than using some random unrelated predictor, predicting wins just from the overall average. So interestingly, if we consider a model with not just offensive total plays in it, but also offensive total yards, what we see is something a little bit weird. Well, if we look at the p-value of the offensive total plays, we see the p-value is 16.7%. So it is not statistically significant. And here, people often get puzzled. How can we have offensive total plays be significant in a simple linear regression, but not significant in a multiple regression model? Shouldn't it be the case that a predictor either is or is not significant, regardless of what the model is? Well, unfortunately, the answer is no. The significance of a model is, or significance of a predictor is model dependent. It matters what other predictors are in the model. Why is this the case? Well, remember what the specific definition of significance was. When I look at the p-value of a predictor, it is telling me the probability that a random predictor would reduce the sum of squared errors when added to a model already containing the other variables in it. So in this case, what the p-value is telling me is that, hey, if I start out with a model predicting wins from the number of offensive total yards, if I add the number of offensive total plays into the model, that does not further decrease the sum of squared errors by any more than what I would expect by chance from a random predictor. It's definitely true that I do better predicting wins using offensive total plays than essentially nothing at all, but it turns out I don't do any better predicting wins if I already know the number of offensive total yards. Adding in knowledge about the offensive total plays doesn't add any additional significant information. So, just a summary of how we explain this apparent paradox where offensive plays is significant in the simple linear regression but non-significant in the multiple regression model. Well, here's what we know. Based on the simple linear regression, offensive plays does contain information about wins because it's significant in the simple linear regression. However, what we also know is that a statistically significant relationship is not necessarily causal. It may be due to a lurking variable. So in this case, what we learned from the multiple regression is that offensive plays does not contain any additional information about wins beyond what offensive yards already provides. So the implication is that yes, offensive plays does contain information about wins. Offensive yards also contains information about wins, but the information they provide about wins somewhat overlaps. Some of that information is in common between the two. Or, in other words, the information about wins provided by offensive plays is redundant somewhat with the information about wins provided by offensive yards. So what we find in the multiple regression model is that once offensive yards is known, we do not need any additional information from offensive plays. All the information that offensive plays had about wins is in effect used up by offensive yards. And we see this actually relatively often. A predictor might be significant in a simple linear regression saying that, hey, yeah, that predictor contains useful information about predicting y, but that information may be redundant with other predictors in a multiple regression model. So when we look at the p-value of that predictor in a multiple regression, we find it's not significant. That just means it doesn't add any new significant information that we don't already know from the other predictors. All right, so back to this example. Summing this up, we know that yes, offensive plays is a significant predictor of wins. It significantly reduces the sum of squared errors when predicting wins relative to the naive model, predicting wins from the overall average. But the amount of additional reduction in the sum of squared errors when we add it to a model already containing offensive yards is not significant. The information offensive plays has about wins is used up by offensive yards, so adding plays into the model doesn't yield any significant new information. Okay, another example, body fat data. We've seen a few examples with this already, some at first counterintuitive behavior that we can explain away. Let's try to predict body fat from three quantities: the tricep skin fold thickness, the thigh circumference, and the mid-arm circumference of a person. Well, if we fit this model and we look at whether or not the model is significant, we see that, yeah, it is. The F value is 21, that's a lot bigger than 1. The P value of this is 7 times 10 to the minus 6, much less than 5%. So the model is statistically significant. There's something in the model that helps us to predict body fat percentage better than the naive model, or a model full of random unrelated predictors. However, when we look at the individual P values, we see that none of the individual predictors are significant. And so most people, they're left scratching their head at this because they don't understand, hey, how can the model be significant but none of the predictors be significant? Well, let's carefully examine what significance means to explain why this must be the case. So how do we explain this paradox? Well, we know that yes, the model is statistically significant. The reduction in the sum of squared errors is unlikely to occur just by chance with random predictors. What we also see is that triceps is not significant in the model, p-value 17%. What does that tell us? Well, it tells us something very specific. It tells us the amount of additional reduction in the sum of squared errors when it's added to a model that already contains thigh and mid-arm is likely to occur by chance, using a predictor unrelated to body fat. So, in essence, the information about body fat that triceps contains is redundant with the information about body fat that thigh and mid-arm circumference contain. Once we know thigh and mid-arm, adding triceps into the model doesn't help us out. That's what it means for triceps to be not significant. Well, going through the other predictors, the same thing occurs. Thigh is not significant in the multiple regression model. Its p-value is 29%. So when we add thigh into the model already containing triceps and mid-arm, the amount of additional reduction in the sum of squared errors is not all that big. In fact, it's readily explainable just by chance. A random predictor could have decreased the sum of squared errors by that much. So, in other words, what this is saying is that the information about body fat percentage contained in thigh is somewhat redundant with the information contained by triceps and mid-arm. If we know triceps and mid-arm, then the information about body fat is exhausted, essentially. The information that thigh adds is nothing new. It's been used up by triceps and mid-arm. All right, and same thing for mid-arm here. Mid-arm's not significant. The p-value is 19%. So what that is telling us is that once we know thigh and triceps, adding in mid-arm into the model doesn't help us to predict Y any better, essentially. All the information about body fat that mid-arm contains is already used up by thigh and triceps, so when we add mid-arm into the model, it does not yield a significant reduction in the sum of squared errors. So synthesizing all this together, essentially what this is telling us is that once any two of those three predictors are into the model, adding in that third variable doesn't significantly reduce the sum of squared errors. It's basically telling us, hey, we only need two of these three. So there's really no paradox after all. Yes, the model is statistically significant. Something about triceps, thigh, and mid-arm is helping us to predict the body fat percentage better than the naive model. And the p-values of the individual predictors is just telling us that, hey, we just need two of the three. Adding in a third variable is unnecessary. The information about body fat that the other two predictors contain is sufficient. Adding in a third variable, regardless of what that third variable is, doesn't really help me out. Okay, well, which ones look like they're, indicative of body fat percentage? Well, simple linear regressions, we see that triceps is a statistically significant predictor. Thigh is also a statistically significant predictor, but mid-arm all by itself is not. Okay, so one thing that we see is that occasionally non-significant predictors all by themselves can become significant when added to a model. We just saw the reverse, essentially. We saw that a predictor that is significant all by itself, like triceps predicting body fat, is not significant when added to a multiple regression model because its information is redundant. So a predictor can be significant in a simple linear regression, but non-significant in the multiple regression when the amount of information it adds is not useful. It's redundant with the information already present in the other predictors. But the reverse can happen as well. So here we're trying to predict salary based on the experience of an individual. And we see that a simple linear regression gives a p-value of 11%. So basically experience does no better at predicting salary than a random predictor. It's just not a good predictor. However, predicting salary from the combination of education, experience, and months says that, oh, well, p-value of experience is less than 5%. It is now a statistically significant predictor. So is this a contradiction? What gives? Well, we've actually already addressed this before. It turns out the effect of experience on salary is relatively small. It's overshadowed by the effect of education and to some extent months as well. So salaries vary a lot in the data set. Most of that variation is attributed to differences in education and differences in months. The small variation that can be attributed to experience gets washed out by these two other variables. It's only when we account for education and months does the association between salary and experience really come through. So experience does contain some useful information about predicting salary. You wouldn't know it if you predicted salary just by itself because its effect is being overshadowed by other sources of variation. But once we account for those other sources of variation, the association stands out. Okay, so here's our overall lesson about the significance of individual predictors. It's tricky and you have to be careful about the interpretation. One thing we saw is that the significance of a predictor and the p-value is model dependent. Whether or not a variable is or is not significant depends on what other predictors are in the model. So when a predictor is not significant, the p-value is 5% or bigger, all that is telling us is that the additional reduction in the sum of squared errors when it is added to a model that already contains the other predictors is not significant. That does not mean the predictor contains no information about y. It just means that any information that it does provide about y is redundant with the information already provided by the other predictors in the model. If a predictor is significant, well, what is that telling us? It's telling us that the additional reduction in the sum of squared errors when it's added to the model containing the other predictors is significant. That does not mean the predictor would be significant in a simple linear regression, because like what we saw with experience, the variation in y attributed to that variable can be washed out or hidden by the variation in y to the other variables. So be careful about significance in p-values. They mean a very specific thing. All right, so we can talk about the significance of a single predictor in a regression model. And if a single predictor is not significant, that means that we could drop it from the model if we wanted. It doesn't add anything to predicting y above and beyond what the other predictors are offering. Now, what if we see a bunch of non-significant predictors? Could we drop them all simultaneously from the model? Well, that actually requires a follow-up analysis. We can't just automatically eliminate all of them at once because we know that p-values are model dependent. Once we eliminate one, the p-values can change, and all of a sudden, maybe some of them, all of them are significant. So here's an example predicting wins from this huge collection of variables. And we see a lot of predictors are not statistically significant in the multiple regression. In fact, x1 is not, x2 is not, x3 is not, x5 is not, and x8 is not. So does that mean I don't need to include those in the model? If I add them into a model that contain the other variables in it, does that help me to predict y any better? Does that significantly reduce the sum of squared errors? To determine this, we need to perform what we call the partial f-test. So the partial f-test will determine the significance of a set of predictors. If it's just a single variable that we're interested in looking at, well, the p-value of that test is already provided for us. It's what we've already been referring to. So, like I said, we can't just automatically drop all the predictors that are not significant since the p-values are model dependent. If we drop one of them, the other p-values might change and they might drop to be less than 5%. So, how do we determine whether or not a subset of the predictors is statistically significant? Well, here's what we do. First, we fit the model that does not contain that subset. So we fit the model and get the sum of squared errors for the simpler model that lacks that set of predictors. Then we add those predictors to the model and find the sum of squared errors there. So the model with more predictors, the more complex model, is going to fit the data better. It has more wiggle room. So there's going to be a reduction in the sum of squared errors when going from this simple model without those predictors to the model with the predictors. And what we're going to do is we're going to look at the p-value of the test. We're going to look at the p-value of the reduction in the sum of squared errors. We know that even if those new predictors that we're adding to the model are completely unrelated to y, that model's always going to fit the data better because it had more wiggle room, so we'll always see a reduction in the sum of squared errors. We need to figure out the p-value of that reduction, the probability of getting a reduction at least is as big as what we observed just by random chance. So what do we say? If that p-value is 5% or greater, the subset is not significant and you can drop all of them from the model without any consequence. If that p-value is less than 5%, the subset is significant and you can't drop any of them. Okay, so for example, let's look at our NFL data set, but let's look at a subset of it actually. I'm going to make a subset called simple wins, which is basically the wins data set, the NFL wins, but without the second, third, fourth, sixth, and ninth column here. So basically I'm taking away those non-significant variables. And so what I'm going to do is I'm going to fit my simple model using that simple wins data set, basically all the variables that were significant in that multiple regression model. Then I fit the more complex model containing all those variables, and then I perform the partial F tests. The syntax is just using ANOVA with these two models, and what I look at is the p-value. What I see is that, yes, there is a reduction in the sum of squared errors. The simple model has a sum of squared errors of 1566. That drops to 1464 when I add in those new predictors into the model. And the p-value is less than 5%. So what I say is the additional 5 variables does add a significant reduction in the sum of squared errors. This reduction of 102 is unlikely to have happened just by chance. So that subset of variables is statistically significant. We cannot eliminate all of them at once from the model. All right, so that will conclude this little bit. Next part up is inferences and making predictions.